So far, we have discussed ion channels that are voltage independent. The channel pore is open at all membrane potentials. These channels are responsible for generating the resting membrane potential of neurons. However, most ion channels in neurons are voltage dependent. Their gating properties depend on the membrane potential of the neuron. We'll be talking about two specific voltage-gated ion channels, the delayed rectifier potassium channel and the voltage-gated sodium channel. And together, these two channels are responsible for generating the action potential in neurons. There are several important characteristics of voltage-gated ion channels that we have to discuss. And the first of these is the voltage activation relation of the channel. Very simply, this tells us at what voltage the channel gates open. And in order to determine this, we can do experiments using the voltage clamp technique. And in this technique, we can set the membrane potential of a neuron to a specific value, and then at that membrane potential, we measure the ions flowing across the plasma membrane. And this tells us how many ion channels are open. So for instance, in the experiment we'll be discussing first, we're voltage clamping a neuron that has only delayed rectifier potassium channels. All the other channels have been blocked by various means. If we voltage clamp the cell at a positive voltage, so we know the ion channels are open, we measure a fairly large current, and using a number of calculations, we can convert this current to the open probability of any one channel. By that I mean that at a positive voltage, the channel has an almost 100% chance of being open. So that would correspond to an open probability of 100%. At a more negative voltage, let's say minus 10 millivolts, the open probability would be approximately 50%. Another way of looking at this is that if there were 100 delayed rectifier potassium channels in the neuron and we were sitting at minus 10 millivolts, approximately half of those channels, about 50%, would be open, and thus the probability of any one channel being open would be 1/2 or 50%. So if we start with a membrane potential of minus 60 millivolts, which is near the resting membrane potential of a neuron, we find that the open probability of delayed rectifier potassium channels is near 0. However, as we depolarize the cell to more and more positive voltages, we see the open probability increase, and when we reach a voltage of plus 20 millivolts or so, the open probability of the channels is almost 100%. Another important characteristic of voltage-gated channels is the kinetics of the gating. This tells us the voltage at which the channel gates open, but we'd also like to know how quickly the channel opens once we have depolarized the cell. And we can determine this by doing a slightly different voltage clamp experiment. This is illustrated in the bottom figure here. We initially hold the cell at a very negative potential, minus 80 millivolts, where the open probability will be very low. And then at time equals 0, we very quickly depolarize the cell to, let's say, plus 10 millivolts. And then we measure how long it takes for the channels to open. And we can see with these delayed rectifier potassium channels, the channels open relatively slowly, and we don't reach 100% probability of being open until about 4 milliseconds. So this slow opening of the channel is why this channel is called a delayed rectifier, because the gating open is delayed. Now, this may seem to contradict something we learned earlier, which is that voltage-gated channels gate from a closed state to an open state almost instantaneously. Well, in fact, there's no contradiction, because what we're showing here is the average opening time of many channels, 100 channels in this neuron. Any one channel would open instantaneously. One channel might open very quickly after we depolarize, whereas another potassium channel might take 3 milliseconds before it opens. So what we're looking at here is the average open time of all of the channels, and we can see that on average it takes a fairly long time, several milliseconds, to open. Another way of characterizing ion channels is to determine the molecules that can block the channel. And in the case of the delayed rectifier potassium channel, tetraethylammonium, or TEA, is effective in blocking the channel. Now, TEA is a positively charged ion. It has a charge of +1, and in fact it looks very much like the potassium ion, except it's slightly bigger. So when the delayed rectifier potassium channel is open, if TEA is present, it will go into the channel pore, but because it's slightly bigger than a potassium ion, it will get stuck and actually clog up, block the channel pore, thus preventing any potassium ions from flowing through the cell. The second voltage-gated channel that we will be considering is the voltage-gated sodium channel. And just as in the potassium channel, we'd like to know what the activation relation for this channel is. And to determine this, we can do a voltage clamp experiment that is very similar to the one we did on the delayed rectifier potassium channel. In this case, we're recording from a neuron that has sodium channels in it, and all the other channels, including potassium channels, have been blocked. So in this experiment, we initially hold the cell to -60 millivolts, again near the resting membrane potential, and we find that the open probability of sodium channels is near 0. As we depolarize the cell to more and more positive voltages, we see that the open probability of sodium channels increases, and as with the potassium channel, when we reach a voltage of +20 millivolts or so, we find that the open probability of sodium channels is almost 100%. So the activation relation of voltage-gated sodium channels is very similar, not identical, but very similar to that of delayed rectifier potassium channels. We then will look at the kinetics of opening, and here we see that the kinetics, the time course of opening of sodium channels, differs very dramatically from that of delayed rectifier potassium channels. We'll do the same voltage clamp experiment to measure the kinetics of the sodium channel as we did for the potassium channel. We first hold the neuron at a negative membrane potential of -80 millivolts, and then at time equals 0 we'll raise the voltage to +10 millivolts. In this case, we see that the activation of the channel occurs much more quickly. It occurs within hundreds of milliseconds instead of hundreds of microseconds instead of several milliseconds. However, we see another striking difference between the behavior of sodium channels and that of delayed rectifier potassium channels, and that is after about half a millisecond or so, the open probability of sodium channels begins to decay. So remember, we have depolarized the cell, and the cell remains depolarized. But even though we're still sitting at a membrane potential of +10 millivolts, the open probability decays, and then within a few milliseconds, the open probability has dropped down to near 0. This behavior is called channel inactivation, sodium channel inactivation, and it's a very important characteristic of sodium channels. And in fact, as long as we maintain a depolarized voltage, the sodium channel will remain inactivated, and the open probability of the channel will be 0. The only way to remove inactivation from the sodium channel is to repolarize the cell back to near the resting membrane potential, and then after a few milliseconds the sodium channel can recover from inactivation and it is ready to be activated again. The inactivation of sodium channels is caused by a mechanism called the ball and chain. And in this mechanism, there is a segment of the sodium channel protein that actually swings into place to block the pore of the channel. And we'll explore this in more detail in the next slide. Just as we found that TEA was effective in blocking delayed rectifier potassium channels, the molecule tetrodotoxin, or TTX, has been found to be effective in blocking the sodium channel. This diagram illustrates the activation and inactivation processes of the voltage-gated sodium channel. We're looking at the channel from the outside of the cell. We're looking down on the membrane, and what we see here is the activation gate of the channel, which is closed. We're sitting at a negative membrane potential, minus 80 millivolts, and at this potential the open probability is near zero, so the activation gate is closed and no ions can flow through the channel pore. We then depolarize the neuron to plus 10 millivolts, and within a very short time period, maybe a few hundred microseconds, the activation gate opens, the pore of the channel is open, and this allows sodium ions to flow from the outside to the inside of the cell. Now, with the activation gate opening, this causes a conformational change in the channel protein, allowing another segment of the protein on the cytoplasmic side of the protein, the so-called ball and chain, to swing into place, and this blocks up the inner entrance to the channel pore. And in this state, sodium ions cannot flow through the channel anymore. This is called inactivation, and in this state, the channel activation gate is still open, but the channel cannot conduct sodium ions because of the block of the ball and chain at the entrance to the channel. As long as the cell remains depolarized, the ball and chain remains in place, and the channel remains inactivated and unable to conduct sodium ions. This can last for however long the cell is depolarized, for many, many seconds. The only way to remove inactivation is to repolarize the cell to a negative potential, let's say near the resting membrane potential. Soon after we repolarize, the activation gate of the channel, the green gate here, is closed, and only after the activation gate closes does the ball and chain swing out of place, and this is recovery from inactivation. And it's only after the ball and chain have been removed can the channel open up and conduct ions once it's repolarized again.